To obtain examples of one-line diagrams for services, specifically 120/208 volts three-phase applications, there are several resources available. These resources include online resources, industry publications, books, and manufacturers' websites. Firstly, let us explore online resources, which include Schneider Electric, Eaton, Square D, AB, and Siemens. Schneider Electric provides a download center where you can find various documents including one-line diagrams. Eaton offers technical support documentation with board layout diagrams which can be helpful. Square D also has a download center with relevant documents. ABB provides a library of resources for low-voltage systems. Siemens offers industry support with access to various documents. Secondly, consider industry publications such as IEEE Standard 399. This standard covers graphic symbols for electrical and electronics diagrams, which are essential for understanding and creating one-line diagrams. Thirdly, you may also want to look into the books available. Electric Power Distribution for Buildings 7th edition by Horst Way and Kim Neitzel is an excellent resource. Also consider Power System Analysis and Design 6th edition by J. Duncan Glover, Milukut Sarma, and Thomas Overby. These books provide in-depth knowledge and examples of power system design, including one-line diagrams. Lastly, consult manufacturers' websites. SHE offers one-line diagrams. Cooper Power Systems provides solutions for substation automation and protection, including sub-one-line diagrams. Legrand also provides a list of electrical solutions. Keep in mind that these examples typically cover general applications and may need modifications to suit specific project requirements. It is always recommended to consult with qualified electrical engineers or manufacturers for guidance on specific applications. A one-line diagram, also known as a single-line diagram, is a simplified representation of an electrical power system. It uses symbols and lines to show the major components and their connections. Understanding one-line diagrams is essential for electrical engineers, technicians, and anyone involved in the design, operation, and maintenance of electrical systems. The purpose of a one-line diagram is to provide a clear and concise overview of the electrical system, making it easier to analyze and troubleshoot problems. It helps in understanding the flow of power, identifying potential faults, and ensuring the safe and efficient operation of the system. Components typically found in a one-line diagram include firstly, generators, which are the sources of electrical power. They are represented by a circle with a G inside. Secondly, transformers, which are used to step up or step down voltage levels. They are shown as two coils connected by a core. Thirdly, circuit breakers, which are protective devices that interrupt the flow of current during fault conditions. They are represented by a rectangle with a switch inside. Fourthly, buses, which are common connection points for multiple circuits. They are depicted as a straight line. Fifthly, loads, which are the devices or equipment that consume electrical power. They are represented by various symbols depending on the type of load. Sixthly, cables or lines, which represent the conductors that carry electrical current. They are shown as solid lines connecting the components. In a 120/208 volts three-phase system, you will typically see these components interconnected to provide power to various loads. The system usually starts with a transformer that steps down the voltage from a higher level to 120/208 volts. The transformer is connected to a main distribution panel, which acts as the central hub for distributing power to different circuits. From the main distribution panel, branch circuits are run to individual loads such as lighting, receptacles, and equipment. Each branch circuit is protected by a circuit breaker to prevent overloads and short circuits. The one-line diagram will show the connections between these components, including the size and type of conductors, the ratings of the circuit breakers, and the characteristics of the loads. To read a one-line diagram effectively, start by identifying the main components such as the generators, transformers, and buses. Then, trace the flow of power from the source to the loads, paying attention to the voltage levels, current ratings, and protective devices. Look for any potential bottlenecks or weak points in the system that could cause problems. Also, pay attention to the grounding system, which is essential for safety. The grounding system is usually represented by a separate line that connects to ground electrodes. Common mistakes to avoid when working with one-line diagrams are firstly, misinterpreting symbols. Make sure you understand the meaning of each symbol used in the diagram. Secondly, overlooking important details such as voltage levels and current ratings. These details are crucial for understanding the system's performance. Thirdly, failing to consider the grounding system. The grounding system is essential for safety and should not be ignored. Fourthly, not updating the diagram when changes are made to the electrical system. The diagram should always reflect the current state of the system. Software tools can be helpful for creating and managing one-line diagrams. Some popular options include AutoCAD, ETAP, and SKM Power Tools. These tools provide libraries of symbols, automated calculations, and other features that can make the process easier and more efficient. They also allow you to create professional-looking diagrams that are easy to read and understand. It's important to regularly update and maintain one-line diagrams to ensure they accurately reflect the current state of the electrical system. This includes updating the diagrams whenever changes are made to the system, such as adding new loads, replacing equipment, or modifying the wiring. Regular maintenance also involves reviewing the diagrams to identify any potential problems or areas for improvement. By keeping the diagrams up to date, you can ensure that they are always a valuable resource for troubleshooting, maintenance, and future planning. Understanding the NEC, or National Electrical Code, is critical when designing and working with electrical systems. The NEC provides guidelines and regulations for the safe installation and maintenance of electrical wiring and equipment. It covers a wide range of topics, including conductor sizing, overcurrent protection, grounding, and wiring methods. When creating one-line diagrams, it's essential to comply with the NEC requirements. This includes using the correct symbols, specifying the appropriate conductor sizes, and ensuring that the overcurrent protection devices are properly rated. The NEC also provides specific requirements for grounding, which are essential for safety. By following the NEC guidelines, you can ensure that the electrical system is safe, reliable, and compliant with industry standards. Here are some key NEC articles that are relevant to one-line diagrams for 120/208 volts three-phase services. Firstly, NEC Article 220 covers branch circuit, feeder, and service calculations. This article provides the requirements for calculating the load on branch circuits, feeders, and services. It includes methods for determining the demand factors, which are used to reduce the calculated load based on the likelihood that all the loads will not be operating at the same time. Secondly, NEC Article 230 covers services. This article provides the requirements for the service entrance conductors, overcurrent protection, and grounding. It includes specific requirements for the size and type of conductors, the ratings of the overcurrent protection devices, and the methods for grounding the service. Thirdly, NEC Article 250 covers grounding and bonding. This article provides the requirements for grounding and bonding electrical systems. It includes specific requirements for the size and type of grounding conductors, the methods for connecting to ground electrodes, and the bonding of metal enclosures and equipment. Fourthly, NEC Article 310 covers conductors for general wiring. This article provides the requirements for conductor sizing, insulation types, and ampacity. It includes tables that list the allowable ampacities of conductors based on their size, insulation type, and ambient temperature. Fifthly, NEC Article 408 covers switchboards, switchgear, and panel boards. This article provides the requirements for the installation and construction of switchboards, switchgear, and panel boards. It includes specific requirements for the overcurrent protection, the arrangement of the components, and the working clearances. Grounding is a critical aspect of electrical safety, and it plays a vital role in one-line diagrams. The grounding system provides a path for fault current to flow back to the source, which helps to trip overcurrent protection devices and prevent electrical shock hazards. In a one-line diagram, the grounding system is typically represented by a separate line that connects to ground electrodes. The grounding line is usually shown with a series of ground symbols, which indicate the connection to Earth. There are two main types of grounding systems. Firstly, the equipment grounding system, which connects the metal enclosures of electrical equipment to ground. This helps to prevent electrical shock hazards by providing a low impedance path for fault current to flow back to the source. Secondly, the system grounding system, which connects the neutral conductor of the electrical system to ground. This helps to stabilize the voltage and provide a reference point for the system. The NEC provides specific requirements for grounding, including the size and type of grounding conductors, the methods for connecting to ground electrodes, and the bonding of metal enclosures and equipment. It's essential to comply with these requirements to ensure that the electrical system is safe and reliable. Let's delve deeper into creating a one-line diagram for a 120/208 volts three-phase service. Firstly, identify the source of power. This is typically a utility transformer that steps down the voltage from a higher level to 120/208 volts. Represent the transformer with its appropriate symbol, including its kilovolt ampere or kvolt amps rating and voltage ratio. Secondly, draw the service entrance conductors. These are the conductors that connect the transformer to the service disconnect. Indicate the size and type of conductors, as well as their ampacity. Thirdly, show the service disconnect. This is typically a circuit breaker or a fuse switch that provides overcurrent protection for the service. Indicate the rating of the overcurrent protection device. Fourthly, draw the main distribution panel. This is the panel that distributes power to the various branch circuits. Show the number of circuits and the rating of the panel. Fifthly, draw the branch circuits. These are the circuits that supply power to the individual loads. Indicate the size and type of conductors, as well as the rating of the overcurrent protection devices. Sixthly, show the loads. These are the devices or equipment that consume electrical power. Indicate the type of load and its power requirements. Seventhly, include the grounding system. This is the system that connects the metal enclosures of electrical equipment to ground. Show the grounding electrode conductor and the equipment grounding conductors. Lastly, add any other relevant information such as the location of the equipment, the name of the building, and the date the diagram was created. Now let's examine the specific symbols used in one-line diagrams. Firstly, a circle with a letter inside, which typically represents generators G, motors M, or other rotating equipment. Secondly, straight lines representing conductors or cables. The number of lines may indicate the number of conductors. Thirdly, a transformer is represented by two coils separated by two vertical lines, which represents the core. Fourthly, a circuit breaker is typically a rectangle with a diagonal line or a switch symbol inside. Fifthly, a switch which is a simple break in the line to indicate a manual disconnect. Sixthly, a bus which is a thick, straight line representing a common connection point. Seventhly, a ground is represented by a series of horizontal lines decreasing in length, connected to a vertical line. Eighthly, a fuse which is similar to a circuit breaker but often depicted as a smaller rectangle with a line through it. Ninthly, a capacitor which is represented by two parallel vertical lines. Tenthly, an inductor which is represented by a coiled line. Remember, accurate and detailed one-line diagrams are essential for the safe and efficient operation of electrical systems. Use the correct symbols, follow NEC guidelines, and regularly update the diagrams to ensure they accurately reflect the current state of the system. Remember, it is always recommended to consult with qualified electrical engineers or manufacturers for guidance on specific applications.